You fell asleep last night, and you cannot say when. You remember lying in the dark. You remember the alarm. Between them is a stretch of your own life you were never present for. That gap is built into the hardware. Deep in your hypothalamus, a piece of brain the size of an almond sitting just above the roof of your mouth, is a circuit designed so that falling asleep has no middle.
Here is the circuit. On one side, a cluster of neurons called the ventrolateral preoptic nucleus. When it fires, it releases GABA and galanin, two messengers whose whole job is telling other neurons to be quiet. Facing it, the arousal system. Histamine, norepinephrine, and serotonin neurons, the cells holding you awake right now. And each side inhibits the other. Each one, as it gets stronger, silences the only thing that could silence it. So there is no comfortable middle setting. Whichever side edges ahead runs away with the whole system. Engineers call this a flip-flop. It snaps, and it does not dim.
The real thing is messier than two boxes. And in a human, the flip takes seconds to minutes rather than an instant. But there is no stable halfway state to park in, and your ability to record anything fails before you would say you were asleep. In sleep labs, people cross the border. Their first spindles appear, and woken a minute later, many insist they were awake the whole time. So what pushes it over? Two things, and they have to agree. The first is pressure. Every second you were awake, your neurons burn a fuel called ATP, and one of the leftovers is adenosine. It builds up around your brain cells for as long as you stay up, and it leans on the sleep side. 16 hours in, that lean is heavy. The second is timing. Just above the point where your optic nerves cross sits the suprachiasmatic nucleus, a clock of around 20,000 neurons wired straight to the light entering your eyes. It does not make you sleepy. It decides when sleepiness is allowed to win, which is why you can be wrecked at 4 in the afternoon and wide awake at 10 at night. Caffeine never touches that pressure. Adenosine works by landing on receptors, the docking points on a neuron's surface. Caffeine sits in them without switching them on. So the adenosine is still there, still rising, simply unread. Then the caffeine clears, often around 5 hours, though it varies enormously, and a full day of accumulated signal arrives at once. That is the crash. You got the bill. One more piece, and it is what proves the switch is real. In the lateral hypothalamus sits a small population of neurons making orexin. Orexin does not wake you up. It rests a hand on the switch and holds it wherever it sits. In narcolepsy type 1, most of those neurons are gone, and you get exactly what you would predict from a switch with nothing steadying it. Sleep arrives in the middle of a conversation. Dreaming starts at sleep onset instead of an hour in. And the paralysis that belongs to dreaming leaks into waking life. So a burst of laughter can drop someone's muscle tone where they stand. So the switch throws, and the night has a program. The first minutes are N1, the handover. The steady alpha rhythm of a relaxed waking brain breaks into slower, ragged theta. Muscle tone falls away. And every so often, right here, your whole body jolts. One hard, involuntary kick that hauls you back. It is common and harmless. One popular explanation is that the brain reads the sudden loss of muscle tone as falling and throws out a catch reflex. That is the leading story, not a settled fact. Then N2, and the brain starts defending the night. Every so often, the trace produces a spindle, a burst of fast rhythm, half a second to 3 seconds long, that swells and fades. Spindles are built by the thalamus,
The relay every sound and every touch passes through on the way to your cortex, and by a thin inhibitory shell around it called the reticular nucleus, which clamps those relay cells in rhythm.
This is what that looks like on a real recording. 30 seconds of one person's sleep, every line a different sensor, and the two short marks are the spindles.
Which is why the same noise does different things at different hours. A door closing at 11 while you are still in light sleep can wake you. The same door at 3 in the middle of a run of spindles does not. To be honest about the evidence, sound still travels up to the cortex during spindles. The sleeping brain is not deaf. What changes is the odds that a sound gets promoted into an emergency. 20 minutes in, the trace changes completely. The fast scribble is replaced by enormous slow rollers, about 1 a second. And they are slow because the cortex has begun firing together. Millions of neurons going quiet, then firing, then quiet, in unison. This is N3, deep sleep. And almost all of it is stacked into the first part of your night. During those waves, your hippocampus, the structure that writes new memories, replays the day in fast, compressed bursts, and the cortex, writing the same rhythm, takes delivery. That transfer is the best supported job any sleep stage has. It also explains why being hauled out of this stage is awful. That thick, where am I feeling after a badly timed alarm. Something else happens down here, and this is where the science is genuinely unsettled. Scans of sleeping people show the volume of blood in the brain pulsing during these slow waves, while cerebral spinal fluid, the clear liquid your brain floats in, surges in and out in large waves locked to the same rhythm. Those waves are real. What they are for is being fought over right now. One line of work says the pulsing drives fluid through brain tissue and carries waste out, and a recent mouse study proposed a pump, slow waves of norepinephrine squeezing blood vessels. Another mouse study measured clearance directly and found it fell during sleep rather than rising. Whether the sleeping human brain cleans itself faster is still an open question. 70 to 90 minutes after you went under, the trace does something strange. The slow rollers vanish, and the line goes fast, low and irregular. It looks almost exactly like being awake. Your eyes start moving in bursts behind closed lids. This is REM, and someone woken here will usually have a dream to tell you about. And underneath that hot brain, the body is being held down on purpose. In the pons, part of the brainstem, a region called the sublaterodorsal nucleus fires during REM. It recruits inhibitory neurons in the medulla and spinal cord, which release GABA and glycine onto the motor neurons that drive your muscles and clamp them shut. Your dream sends the command to run. The command reaches the spinal cord and dies there. Two things are exempt: the muscles that move your eyes and your diaphragm, because you still have to breathe. That clamp is machinery, and machinery has failure modes. Sleep paralysis is surfacing while the clamp is still shut. Awareness comes back, the body does not follow, and for perhaps 30 seconds, you are awake and unable to move. It is more common than people think, and knowing it is the break taking a moment to let go makes it a great deal less frightening. The opposite failure is REM sleep behavior disorder, where the clamp does not hold and the dream gets acted out. Doctors take confirmed cases seriously because a substantial share of those diagnosed go on to develop Parkinson's disease or a related condition years later. That is a diagnosis made in a sleep laboratory and a different thing from talking in your sleep. Anyone genuinely worried about what they do at night should take it to a doctor. Now stand back, because the last thing the switch explains is the shape of the night. The cycle repeats roughly every 90 minutes.
but what is inside it changes. Deep sleep is front-loaded. The biggest slow waves come in the first couple of cycles and are largely finished by halfway. REM does the reverse. The first period can be a few minutes long, while the ones near morning run half an hour or more. So a night cut short is not a shorter version of a full night. Sleep 4 hours and you keep nearly all your deep sleep and lose most of your dreaming. The 2 hours you skipped are where a large share of the REM lived. It is also why your most vivid dreams are the ones just before you wake up. And tonight, it happens again. Adenosine climbs, the clock opens the gate, and the two sides lean on each other until one of them wins. You will not be there for it. You never are. The circuit is built so there is nothing in the middle to remember.